तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The last lecture we looked at the timings of flip-flops. In the lecture before we looked at the different types of flip-flops. So, the last two lectures basically we have been covering flip-flops, and as we said earlier, flip-flops are essential for sequential circuits, but they alone do not constitute sequential circuits. Of course, there are exceptions like counters where only flip-flops are used. But in general, any digital system will have both combinational and sequential logic, and sequential logic uses flip-flops. Even though they are total digital systems, whenever a sequential component like a flip-flop is involved, the circuit is called a sequential circuit, even though it will have a combinational logic in it. So, today we will see circuits which will use both combinational and sequential elements. As I said, they are called sequential circuits, but they will have both combinational elements and sequential elements. Combinational elements can be in terms of gates and multiplexers, PLAs, PLDs, whatever, and sequential circuit element will be flip-flops. So, to give you an example of this, I will first take a very simple commonly used circuit. You are also familiar with this, a full adder. We have seen a full adder earlier in books, also in the earlier course. Even in this course, in the combinational logic, we looked at full adders, implementation using multiplexers, full adder implementation using decoders, and even program logic device. Now, these are one bit full adder in the sense when you give a bit A and a bit B along with a carry bit from the previous position, you get a sum and a carry. It is a single bit combination logic, and you want to have many bits to be added at the same time. You will have to have several of these working in parallel. That means, if you want to do a 4-bit addition, you need 4 full adders connected in cascade. On the other hand, if you have only one full adder and you want to add 2 numbers which are more than 1 bits, multi-bit numbers, we go in for a technique called serial adders. That means, the same full adder will be used repeatedly for adding different bits of A and B. So, this is how it is going to look like, the 1 bit full adder. With 2 elements and the sum. But we know that 1 bit full adder requires, in addition to this A and B, let us call this AI and BI, and this is SI. This is what we have used in the previous lectures for the signals of full adders. We also in addition have Ci minus 1, the carry from the previous bit position and the carry from the output for the current position. So, this completes the full adder, but as I said I am going to use the same full adder. First I will add a bit, let us say it is 4 bit number A0, A1, A2, A3, B0, B1, B2, B3. First I will add A0 and B0, then I will add A1 and B1, then A2, B2, then A3, B3. While doing so, I should retain the carry from the previous position and put it back here. This is exactly the concept of sequential circuit we have seen in the last lectures. Last 2 lectures we talked about the sequential circuit requirement being a device or a circuit element which will store a value from the previous clock period and give it as the input to the system during the next clock period. So, the storage element is required, which we will not see in a combinational full adder. That is why I want to take this example, because all of us are familiar with full adder. It is a simple circuit. Same time, how do you introduce a combination sequential element in this full adder? So, what we have to do is, that means take this Ci, keep it in a flip flop, D flip flop, and connect it back as the input. So, the carry does not come from anywhere, it only comes from within the circuit. Now, as each bit is placed here, first of course we will have to reset the flip flop so that the flip flop Q will be 0, so there is no Ci minus 1. So, first 2 bits come, gets added, there may or may not be a carry that gets stored here, and that becomes the Ci minus 1. Second bit A1, A2 comes, A1 and B1 comes, the second bits. At that time Ci minus 1 will be there, in this case 1 or 0 depending on the previous bits S0, B0, that gets added, generating a new Si, a new Ci, that gets stored and so forth, and it can go on. So, we do not have to be, we are not restricted by the number of bits to be, the hardware does not restrict the number of bits to be added. Whereas in a combinational full adder, if you want to add a 4 bit number, we need 4 full adders, 4 1 bit full adders, and if you want 8 bit adders, 8 bit addition, you need 8 1 bit full adders. So, we will have to tell in advance how many things do you need. Here I can use this repeatedly as long as I want. Of course, there are some practical considerations. Where is this Ai going to come from? Where is Bi going to come from? Where is Si going to go to? All those questions will be answered. There have to be registers to store all these things. So, we will have a register here. I am freely using a lot of these components which are not exactly defined earlier in this course, but as I said, this is a second course and all of you are familiar with these things. So, there is no point in trying to be very legalistic about it. Whatever has not been defined earlier should not be used. If I use that concept, then we can never proceed. So, I know that all of you know registers and shift registers from the previous course in digital circuits. So, I am going to use a shift register here, wherein originally I am going to put my entire A number, whatever is the number of bits, B, whatever is the number of bits, and I am going to put this result also in a shift register, wherein as Si gets, this gets stored and gets shifted along the way. So, I will say at the end of it operation I will take S from here, and if I provide sufficient number of bits here, the loss carry also will be taken into account. So, I do not have to provide an extra register for carry. For example, if I have a 2 4 bit adders, 4 bit numbers, I may have a 5 bit, some maximum of 5 bits. So, that means I provide for 4 bit shift registers of inputs, I will provide a 5 bit shift register for the output. So, the last bit also will get added here, the carry, last carry will be added here. So, we do not have to worry about carry being separately saved and used, and all of them have to be clocked properly. So, we need a clock anyway for the flip flop. When does the flip flop know it has to release the previous value, or when does it know that it has to store the new value, the new value of Ci and rewrite on the old value? That will be decided by the clock, the same clock which can be used for shifting the shift registers. So, I will say that there will be a clock and the same clock can also be used for this output shift register. So, this is one clock which shifts bit A into the full adder, bit B into the full adder, shifts Si to the sum register, stores the carry value to be used as the Ci minus 1 for the next bit addition. This is a sequential circuit design, the concept of sequential circuit. I just brought this up because it is not today, full adders are so inexpensive. You know, a full adder consists of 2 exclusive OR gates for the sum and a 3 2 input AND gates and a 3 input OR gate for the carry, and it is not a huge hardware, and you can multiply it any number of times in order to carry out a large addition, plus the fact this also delays the addition process. We are talking of gigahertz or megahertz, several hundreds megahertz operation, that means the clock speed is very high. So, if I have this type of full adder, number of bits, the total time it takes for me to complete the addition is going to be that many clock cycles. If there are n bit addition, I need n plus 1 really, because the last one carry out, maybe there will be last carry out which has to be added and put here. So, if there are n bit addition, I need n plus 1 clock cycle to complete this operation. It may be too slow for our modern technology. So, today's technology requirements are, can you trade the speed with hardware? If I can give you more hardware, called hardware accelerators, people call it, you might have heard of this term, frequently used today in technology. Hardware accelerator means, can I provide hardware and speed up the process. So, trading the hardware for speed, can I get more speed if I give you more hardware? But on the other hand, you want to reduce the hardware for real estate, size of the chip. So, there are conflicting conditions. This is all we will have to discuss as we go along in this course. There are power requirements, speed requirements, space requirements, all those things will be taken into account. So, each of these cannot be analyzed in completely like that. Each is a separate concept available to you. If you want to use it, if you do not want to use, you do not want to use it. I took this example simply for 2 reasons. One is a full adder is a very familiar example to all of us. Second thing is, we talked about sequential circuits and we talked only about flip flops, but I gave you the model of the Mealy circuit and Moore circuit yesterday, saying that a Mealy or a Moore circuit will have inputs, state variable, output and state variable. So, this concept I want to explain, and what better way to do it than having a very simple circuit explain it. Now, if you take our Mealy model of yesterday's lecture, the last lecture, we had this external inputs. In this case, what are the external inputs? Ai and Bi, and I said state variable input Ci minus 1, output is Ci, Si, and the state variable output is Ci. So, there is a one state variable input which is again delayed by a flip flop. Oh. See, this concept of flip flop output, the state variable input getting resulting in combinational output and state variable outputs. The state variable output used as state variable input again for the next clock period along with the new set of inputs A and Bi. This combination, this model we discussed in the last lecture. So, I thought I could give this example, so it is fit into this. You see, this is the combination logic, this is comb logic. Here in this case 1 bit full adder is a comb logic, all of you know that 1 bit full adder is a comb logic with, as I said, 2 exclusive OR gates and 3 2 input AND gates and 1 3 input OR gate. And then the flip flop here, the combinational inputs are A, Bi, combination output is Si, state variable input is Ci minus 1, state variable output is Ci. To give this one exact mapping using a very simple concept, I brought this today. Of course, I am not going to derive this state map, and I can also prove how to do it by deriving this what is known as a state graph. All of you know what a state graph is from your previous course on digital systems. So, I have a state graph drawn for this circuit and design this circuit starting from the conceptual level. Supposing I do not know this architecture, I just developed this, I did not develop the architecture, I just drew this architecture, I just assumed this and then said that it is going to do a full addition. I explained how it adds, how it acts as a bit serial adder, and I just compared it to the standard architecture and proved it is the same. But it is not the way you do it in a circuit is unknown to you, the system is unknown, the problem specification is new to you, you do not simply draw the circuit configuration, you have to develop the circuit configuration. For that you have to go through the state graph. You start from a state graph and then from state graph you implement the circuit which will also have the same model. Since it is a full adder, I did not do that. I did not want to start with a state machine concept with states in A and B as inputs, C as inputs and S and C as output and all that. I did not want to do that because it is a overkill of this problem. It is a very simple problem, all of you are familiar with. But we will take a slightly more complex example to prove that point. We should also know how to develop a design from a specification when the circuit is not as obvious as this. This is a very obvious circuit. When the circuit is not as obvious as this, we should know how to develop that circuit from the start. We will be able to do the state graph, we will have to understand the problem specification, from the problem specification draw the state graph, from state graph we go to the state table, from state table we get the hardware, and then hardware also have the same architecture, same type of connectivity, the modular architecture will be identical. We will prove that with a slightly more, it is not going to be a very complex example, take a slightly more involved or complex example for this purpose. One of the things which is normally done in digital circuits systems is to compare patterns. This pattern comparison is very useful in many places. Suppose you have a, even the computer password checking is a sort of a pattern comparison. You type a password, of course the password is alphanumeric, assume for a minute it is only a binary password, zeros and ones, one pattern, and let us be verified with the computer will verify your password, the registered password, and then if it matches it will give you access to the machine, otherwise it will deny the access. Of course it can be done in alphanumeric sense by having each of these alphanumeric characters translate into binary. Another place is you can have a combinational logic, combinational lock. Supposing I have a pattern, supposing I have a key, I have this number locks you are familiar with, I can have a similar number lock digitally. Suppose I have a lock in which I know the pattern, only when I put the proper pattern and press a switch, it will give a relay will be operated and my door will open, a latch will operate, my door will open, otherwise the door will not open. So there is another place where you can use a pattern matching. Or sometimes when you are receiving data, you match the data with a given pattern to see whether there is an error in the data. So there are several places, many places where pattern matching is required in digital circuits. So I will take pattern matching as an example for design of a sequence circuit. That also will give you a methodology of the design starting from the specification of the problem through the state graph to the hardware. So, I will say pattern identifier, whatever, I do not know, you can call it anything you like. All it does is to compare whether a particular pattern has occurred. If a particular pattern has occurred, it has to give an output. If in the absence of in the absence of an output pattern, not the given pattern not occurring, it should not give an output, the output should be 0. Basically, the circuit should consist of a single input, make it simple, I am making it simple for you, single output, I will call this X, I will call this Z, and that is a clock. With every clock pulse or clock edge, because as I said yesterday in my last lecture on flip flops, I said this arrowhead points to a edge triggered flip flop, positive edge triggered flip flop. So, for every positive edge of the clock, one bit of the X will be the input to the circuit, and as the inputs occur, there must be some mechanism inside to get those inputs stored, and then when the particular pattern occurs, that pattern will be matched and then output will be set. Now, let me say for example, I want to detect a pattern of 0 1 1 1. Or 0 1 1 0, pattern to be identified, bit pattern to be identified, 4-bit pattern, zero 1 1 0. Now, as the bits keep coming, whenever this pattern occurs, Z output Z will go 1 along with the last 0 of that pattern. I will give you an example. Let us say X is a serial in time, it occurs like this 0 1 0 1 1 0 1 1 1 0 0 1 1 0 0 0 1 1 1 etc. That means each clock pulse one input bit occurs at the input, and the output should be, initially we assume the output is 0, it is called reset condition. Initially there is no output. As the bits keep coming, there will be no output here, the output will be 0 0 0 0 0 0 1 1 1 0 has occurred. Now, this is one of the patterns required. So, a 1 should occur, that is what I mean by the last 0. You see, you remember that this is time is going this way, that means first a 0 was received, then a 1, then a 1, then a 0. The 4th bit corresponds to the output bit. Along with the 4th bit 0, I should get an output of 1. Then of course, it will go 0 0 0 0 0 0, this again will give me 1, let me make a change in this pattern too. give you an interesting concept. I will make it 1 1 0 like this. So, now the fourth bit was a 0, so a 1 was occurred, then the next again is a 1. Now, the question is you have to ask the, as a designer you should ask this question before you start with the design. If this 0 has already occurred and this one is occurring next, should I count this 0 also as into a new pattern? There are two ways of doing it. If I say after every output is generated, you start afresh, you reset your system and start afresh. If you want to do that way, then I do not count this 0, then I will start with the 1 as the next bit. But sometimes you may have to do the overlapping. That means even if this 0 has been counted in this previous pattern, it should still be counted in the next pattern. If that is the specification, then I should count this 0. So, let me assume that model wherein I am going to count this 0 also into my next pattern. So, this is called overlapping. Even overlapping bit pattern should be identified. So, that means my problem has to be very completely and clearly defined. So, I will have to say overlapping pattern should also be overlapping patterns should also be identified. If you say that, then you are very sure of what you should do. If you are not given this, then you are not sure whether I should count this 0 as a new pattern or consider this closed and start again here. Since I am not very specifically saying overlapping pattern should this, see, the specification is very important. If the specification is not clearly mentioned, your circuit performance is not circuit performance has ambiguity. Then later on when some input condition occurs and output is not satisfactory, then they will blame the designer. So, it is the designer's fault if the specification is not completely received. You should ask for the specification. Of course, it is when the person who asks you to design, the person should specify all these specifications, should give all the specifications completely. But in case it does not give, it is your duty as a designer to ask for it and get it. If you also assume something vague and your vagueness is different from the vagueness of the designer, the specifier, a specification giver has a vagueness built into its specification and your design has a vagueness built into your design, but these two vaguenesses do not match, then comes all the problems. Then come all the problems. So, now 0 1 1 0. So, I am going to call this as a new pattern and give one. This is what I wanted to say. Then afterwards of course zeros. So, one input, one output, one clock, of course there is only one clock, inputs, outputs, whenever 0 1 1 occurs, 0 1 1 0 occurs and output C should be 1 and it should be overlapping also should be occurring. Now, this is the problem statement. Now, I forgot one small thing about my previous example of the adder. I said all about the adder being a combination logic and a sequential logic together and all that, but we also defined two different types of sequence circuits in the last lecture. One is a Mealy circuit, the other is a Moore circuit. In a Mealy circuit, output depends on the state and the present state and the inputs. Moore circuit, the output depends only on the state variables. The inputs, external inputs do not come into the picture for the output definition. Output will be decided by the states alone, which are of course defined by the input variables. Outputs or state variable outputs are functions of input variables and the present state variable, that is the next state variable, that defines the output in the Moore circuit. In the Mealy circuit, in addition to these outputs, they can also have outputs which are directly related to the present state and the present set of inputs, and according to that definition, this comes as a Mealy circuit. So, in any circuit that you are designing, so possibility of designing it as a Mealy circuit or a Moore circuit. Mealy circuit is slightly easier to implement. hardware wise it is slightly less complex. Moore circuit is one which is slightly more involved in the hardware. Of course, it is not complex in the sense that it requires a little more hardware, but later on we will have occasions to again come back to this point of Mealy and Moore. Why I am emphasizing on this point here is later in our series we are going to talk of situations where we have to definitely go for a Moore circuit for some reasons. We will talk about it at that time. Because of that, I am always pointing out wherever it is possible there is a Mealy circuit and Moore circuit. So now the question is, should I design as a Mealy circuit? Since I did not design this, I took the circuit and then tried to explain it, so I did not ask this question in the beginning. So later on I realized it is a Mealy circuit. Now in this case, since I am going to design the circuit, before I start with the design, the first question, one of the first questions I should ask, along with the patterns and overlapping etc., all the specifications, one more question I should ask the designer, the person who gives me the problem is, do you want it as a Mealy circuit or a Moore circuit? So let us say make it simple again. As I said, Mealy is slightly simpler than Moore. The whole idea is to make this first example simple, so I am going to call it a Mealy. I am making your life and my life easier by doing this concept. Now with this example and this specification and being a Mealy, we will try to put the state graph. That is the first requirement. Start with the state graph. A state graph will have several states. Again, I do not have to explain the state graph to you. I always keep insisting this is not your first course on digital, this is a second course on digital circuits, because of the flavor we are going to add in this course as VLSI circuits, plus the fact I am directly going to some design rather than going through all these basic things. So I am assuming so many things. Wherever I am assuming things which you do not know, it is your responsibility to catch up, either by reading a book or doing whatever you want to, practice some exercises, browsing through your class notes or looking at a video course or whatever. It is up to you to get to speed about these things, because if you keep missing all these things, later on you will find the whole concept so fuzzy, then you will not be able to appreciate the contents of this course. So I am not going to explain to you what a state graph is, I am going to directly start doing it. So let us assume the first, there is a state called S0, which is a reset state. As I said, you have to start with the reset state with output is 0. So I will make a note here, S0 is reset state. Then in each state the input can be 1 or a 0, that is all. There is only one input, one output. So input is 1 or input is 0. If the input is 1, it does not even fit into my, what is my pattern I am trying to identify? 0 1 1 0. Remember, this is the pattern I am trying to identify. If the very first bit is a 1, it does not fit into the pattern. I do not have to do any work. I do not have to remember this 1. This is I can still remain in reset state. As long as I am concerned the 1 received is equal to not receiving anything, I can continue to be in reset state. So if a 1 occurs, I am here, same state, not producing any output. You know how it is done. First you write the input and next the output. So when you say 1 0, it means x slash z. Input and output are shown with a slash in between. On the other hand, with a 0, it is possible that it is beginning of a pattern. It is possible. It may not materialize as a pattern, but you should not lose it. A 0 has to be captured and kept. You have to remember it. So if the 0 occurs, I will still have no output. Output will come only with along with the fourth bit. So output is still 0, but I need to go to a new state which will remember this. So let me call this S1. S1 is a state will remember 0. S0, remembers S0. So, I have exhausted in S0 what happens if 0 is input, what happens when 1 is the input. Likewise, I have to do from each state S1. In S1 state, if a 0 occurs, I do not have to store it again. So, only already I have stored in S1 is a state where 0 has already been memorized. 0 is recorded when I am already in S1 state. There is no point in recording the second 0 because my pattern requires only one 0. The latest 0 can be taken as the 0 of the pattern and discard the previous zeros. So, that means if 0 occurs, I continue to be in this state. And if a 1 occurs, then you are in business because 0 1 is the likelihood of a pattern being formed. So, if a 1 occurs, I will go to S2. Again output is 0 because I have only received 2 bits so far, no question of output being 1. But I should remember this 1 0 as a distinct pattern which has emerged so far, which may be useful to identify my final pattern. So, my S2 is remembers state which remembers 0 1. Again in S2 what happens? In S2 if 0 comes, that means it will be 0 1 0, no point. If a 0 occurs in S2, I will as well go back here and remember the last 0. It is something like I have received a 0, a 1, I am expecting an extra 1, but 1 has not occurred, a 0 has occurred. What do? I discard my 0 1 earlier and I now start this with a 0 as my beginning, new beginning of a pattern. So, when a 0 occurs, I go back to S1, then output of 0. On the other hand, if 1 occurs, then it could be 0 1 1, could be the 3 bits of the final pattern we are looking at. So, if a 1 occurs, I go to state S3. State which remembers, which will remember 0 1 1. Pattern 0 1 1 has occurred. The fact that you are in state S3 means a pattern 0 1 1 has been identified. All it needs is another 0 to complete the operation. If it is not, of course, you will not get the output as 1. So, in state S3, if 0 occurs, what happens? We are completing the process, good, we will output a 1. But also we have to remember it is an overlapping pattern. This 0 is the last 0 of the first pattern, also will serve as the first 0 of the next pattern. So, the 0 not only should produce an output of 1, should also be remembered as the first 0 of a next pattern. So, what is the state which remembers the first 0? S1. S1 remembers the first 0. So, when 0 occurs in S3, you go to S1 so that that 0 will be remembered as the fresh 0 of a next pattern. At the same time, I should get a output of 1, not a 0. This is the first time or the only time the output will come. So, this is 0 will occur, the output will become 1. If on the other hand, when you are in S3, 1 occurs, you are already in 0 1 1, the 1 occurs has no meaning because I cannot use any of these things, because 0 1 1 1 has no place in our pattern detection. That means it is as good as going to the reset state. If 1 occurs in S3, is a wasted effort, all the things we have done, something like the whole thing was almost there and you missed it. Go back to the reset state with a, it's very simple. I made this circuit specifically simple so that you can understand the concept well. You can practice more such problems. There are any standard textbooks on digital design will give you problems for this type of exercises, for this type of problems. So, you can go and do some of those more complex ones with more number of states and more number of inputs and more number of outputs to get your practice skill on this design of the sequencer circuit. So, what we are having is now a sequencer circuit in which there are 4 states S0, S1, S2, S3, and this is how you write the state table. what is the present state in which the circuit is? What will happen to the circuit next state if the input is 0 and if the input is 1? And what will be the output in each case? That can be written now from this state graph. If the present state is S0, 0 occurs, we go to S1. If 1 occurs, we remain in S0. Either case the output is 0. If state S1, the input is 0, you remain in S1. Input is 1, you go to S2. Both case output is 0. S1 to 0, S2, S1 to S1. You are in S state S2, input occurs 0, go back to S1, and if it is 1, you go to S3. Again, in both cases the output is 0. Finally, when the circuit is in S3 state, input 0 occurs, you go to S1, circuit goes to S1, when 1 occurs, circuit goes to S0. In the first case the output is a 1, second case the output is 0. This is the state table. Again, it is a concept well known to you from a previous course on digital systems, but I thought it is better to do it. So, this is the graph, this is the table. From this table you can get the circuit. How do you do that? You have to assign variables for each of these states. You can arbitrarily assign 0 0, 0 1, 1 0, 1 1 as the state variables. So, we can translate this into a table called transition table. The difference between a state table and a transition table, if you do not know already, is the fact that in state table you refer to the states as symbols S0, S1, S2 or A, B, C, P, Q, R, X, Y, Z. In a transition table you give the actual values of 0, 0, 1, 1, binary values for the states. So, these are the binary values. So, let us call these binary variables what? A and B. Present state again, input, next state, output, present state I will call it AB, input is X, next state is AB again, but then in order to differentiate between the next state and the present state, it is always usual to put a plus on this, output is Z. So, now the present state is 0 0, input is 0, 0 0, input is 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. The next states are S1. S1 is what? S1 is 0 1, 0 1, S0 is 0 0, 0 1, 1 0, 0 1, 1 1, 0 1, 0 0. These are the next states, and the corresponding outputs are 0 0 0 0, 0 0 1 0. So, this is a transition table from which you can draw the corner maps for each of these variables A and B and the output Z, and then implement it in terms of a circuit. After drawing the transition table, we need to realize the circuit, and the best way to do it is to use corner maps if you are going to go for gate implementation. This being the first example and a simple example, we will go for gate implementation of combination logic, which means I will go for corner map, minimize the corner maps and minimize the corner maps to get the minimum expressions for the values, next state variables A plus B plus and the output C. So, these are the corner maps for you do not have to spend a lot of time on this because you know how to do this. We have the transition table here, and all you have to do is to map this transition table into 3 corner maps, one for A plus, second for B plus, third for Z. That has been done here, and I got the expression. These are the 2 terms for which the output is 1, the rest are zeros. So, A plus is this or this is A bar B x, this is A B bar x. So, this x are x and A are A exclusive or B. This is simple equation, this is much simpler, B plus, the whole thing is 1, which is nothing but x bar, and this is A B bar, and Z there is only one term. For Z only one term is a 1, all of this is 0, this happens to be A B x bar. So, with this I can draw the gate structure for this. So, there are 2 flip flops, one of them is going to be called A, the other is going to be called B. So, what I mean by A bar is the input to the flip flop A, that is A plus, the output is A here. Similarly, the input to the flip flop B is called B plus, output of this is B. So, what is A plus? A plus is x, that is A exclusive or B, ANDed with x. B is x bar, or A and B bar. B bar need not be created because B bar is here, you do not need an inverter for that. So, B bar is here, A is here, put them in an AND gate, combine the 2 in an OR gate, you get B plus. These are flip flops, so you need to clock them. And output C is A B x bar. So, A is here, B is here, x is here. So, x has to be put through an inverter. We already have an inverter here if you want to use it directly. X bar, this is my Z. This x bar comes from here. I am not showing a separate inverter. So, actually if you want you can show it in x as an inverter, but that inverter can be saved because we already used an inverter for x. So, now this is the sequential circuit implementation of the original pattern generator we started with. We wanted to generate, we want to detect a pattern occurring as 0 1 1 0, and if it is overlapping we need an extra what all including overlapping pattern we should detect, and whenever the pattern is detected along with the last bit 0 we need to hit a 1, and all that is gotten into this. So, this whole thing is now the Mealy circuit. So, we can the inputs are A, B and x. A, B are the state variables, x is the input variable which is going here, A, B are the state variables. So, we combine x, A, B to get A plus B plus and Z. This is a typical Mealy circuit because output combines the present state variables and the present input, and the next state variables are obtained here using flip flops which are fed back as the clock. This is the clock will be shown here. That's all right. So this just to show that this is exactly the pattern of this, the architecture, the configuration of this circuit is same as the configuration of this circuit, which we started with. So whatever the design problem, whether it's a simple full bit serial adder, simple serial adder or a pattern generator or any other complex problem, the whole thing will come by we can go through the design procedure, remember to have the specifications complete in detail, very clearly written, no ambiguity of the specifications, and then from the specification you draw the state graph. From this state graph you go to the state table, from the state table go to the transition table. Transition table you map into hardware. Hardware there are options, this is only a simple option, gate oriented. Combination logic can be implemented using multiplexers, you know that. Programmable logic devices, there are so many other ways you can implement that. Whatever is the choice you want to make, you make that choice and implement it. And there are some other techniques by which without drawing the state graph, but equivalent method, not that the procedure, conceptually the procedure is same. There are certain ways in which you can do this without having to do that. We will see that later on, but right now this procedure is complete. We will see more examples in future lectures.